Hi everyone, welcome back to Dave's Math channel. This is my 11th video on derivatives, which is a sub-series of my series on first year calculus. Today I'm going to talk about derivatives of exponential functions. And there's kind of two different kinds of exponential functions. There's a to the x, where a is an arbitrary positive real number. And there's e to the x, where e is a special number known as Euler's constant, approximately 2.71828. And these are the formulas. You don't have to worry about the formulas on the bottom here. We're going to talk about the formulas on top. And as you can see, they have very simple derivatives. I mean, in particular, the derivative of e to the x is itself. And up to a multiplicative constant, e to the x is the only univariate function with that property. So it's a very special function. And then it's equal to its own derivative. And a to the x is sort of like that, where a is an arbitrary positive number. It turns out that it's equal to its own derivative. It's just you have to add a multiplicative constant, and that multiplicative constant is the natural logarithm of a, or natural logarithm is the inverse of the exponential function. So anyway, that's what we're going to prove. So anyway, here's just the formulas written out a little larger. And don't worry about the formulas on the bottom. I mean, formulas on the bottom are kind of obvious. This is just if you were using the chain rule. So if you had a function e to the u, where u could be another function of x, well then the chain rule just says that the derivative of e to the u is e to the u times du dx. And similarly, the derivative of a to the u is a to the u log a, because that's the derivative of a to the x. But then we have to multiply by du dx by the chain rule. So that's all that's saying. So anyway, we really just want to derive the two formulas on top here. So here's the proof. I mean, there's a lot of different ways to prove that e to the x is equal to its own derivative. I came up with my own. This isn't the usual way to prove it. Sometimes people prove it by, first deriving a form for the derivative of the natural logarithm. I haven't talked about logarithms yet. I'll do that next time. So I'm doing this a little bit differently than how most other people derive this. And there's another way to derive this formula where you first have to prove that the limit of a derivative of e to the x when x equals 0 was 1. You can get it that it's equal to e to the x up to a multiplicative constant, but you also have to prove this limit, that the derivative as x approaches 0 of e to the x is equal to 1. In other words, the slope of the exponential function at x equals 0 is 1. That's another way you can do this, but I don't want to do it that way. I came up with my own proof here. And I'm pretty sure other people have proved it this way too. So anyway, let's just do it this way. So I'm going to start with a definition of E. And I'm not going to prove this limit. This is a limit formula for E. You can even regard this formula on top as a definition of Euler's constant E. It turns out you can define E to be the limit as n goes to infinity of 1 plus 1 over n all raised to the nth power. And I have a video on this, so I'm not going to go over this formula. I have a nice video on E and how to define it this way. You can look at this from the point of view of compound interest, which is usually the way I think people first define E. Anyway, E is a very, very useful math concept. It's probably second to pi. I think pi and E are probably the most important irrational numbers in math, and I think E is second to pi. But anyway, so E has this definition. So that means e to the x. We can just take this limit, which is our definition of E, and raise that to the x power x. And you know that when you exponentiate twice, that's like multiplying the exponents. So we can rewrite the e to the x as this new limit. The limit as n goes to infinity of 1 plus 1 over n all raised to the power nx. And we can change variables. We can call m nx, and then that means that n is equal to x over m, which means 1 over n is equal to, or I add it backwards, n n is equal to, n is equal to x over m, so 1 over n is equal to m over x over m. So the bottom formula, it's just the limit is m approaches infinity of 1 plus x over m to the m. Now we can use that. We can use this formula for e to the x. We can differentiate that just using the power rule and the chain rule. So let's do that. So we have enough machinery now to compute the derivative of e to the x. So let's do it. So we write e to the x as a derivative of this limit, and we can switch the order of derivatives and limits. So it's just the limit of this derivative, the derivative of 1 plus x over m to the mth power. That's nice because we know how to compute this derivative. We use the chain rule and the power. So let's do that. So this is like the derivative of f of g of x, where f of x is 1 plus x over m, and g of x is x to the mth power. And so we're going to first get f prime of g of x. That's just m times 1 plus x over m to the power m minus 1. That's just what you get from the power rule. But now we have to multiply that by g prime of x. Don't forget that g of x was 1 plus x over m. That means its derivative is 1 over m. So now this is kind of nice. We have a factor of m and a factor of 1 over m multiplying each other, so they cancel. And we're just left with the derivative as m goes to infinity of 1 plus x over m to the m minus 1. And then we can just do a little manipulation here. You know that this is a product. We can write this as the limit is m goes to infinity 1 plus x over m to the minus 1 times the limit is m goes to infinity 1 plus x over m to the m. We know what the second factor is. It's just e to the x, because that was the formula we derived above. But then we also know what this first limit is, because m is going to infinity. That means that x over m is going to 0. Whatever x is finite. So x over m for sufficiently large m is going to go to 0. That means we have something that's approaching 1 raised to the power minus 1, and we don't care about minus 1. It's just something that gets very close to 1, and we're taking its reciprocal. So that thing is also going to be close to 1. So the first limit is 1, and the second limit is e to the x, and 1 times anything is the thing. So that's just e to the x. Voila. That's a proof that the derivative of e to the x is equal to e to the x. A little more complicated than the proofs you usually see, but we had all the tools to do it, so I just decided to do it this way for fun. Like, there a lot of times in math, there's different ways to arrive at the same results. So I just decided to do it a little differently, I guess. And then once we have this result, it's pretty easy to prove that the derivative of a to the x is a to the x times the natural logarithm of a. How do we prove that? Well, we can start by rewriting a to the x as, we start with a. We know that a is equal to e to the log a. That's true for anything because the natural logarithm is the inverse of the exponential function. So the exponential is just undoing what natural log does. So in general, for any number a, any positive number a is equal to e to the natural logarithm of a. That's just an identity. You might have seen this in high school, I'm not sure. Or maybe you saw it with different bases besides e. I mean, in general, I don't want to get into that. But anyway, it's true. So we have e to the log a, all raised to the x power. We can use the rule for exponentiating powers. Let's just multiply the powers. We get e to the x log a. So now a to the x prime is the derivative of e to the x log a. We can use the chain rule again. We can let f of x be e to the x and g of x be x log a, x ln a. And so now we're going to apply the chain rule. Here we go. Derivative of a to the x is equal to the derivative of f of g to the x, f of g of x, and that is equal to f prime of g of x times g prime of x. That's just the chain rule. And f prime of x is I said f of x was e to the x, f prime is also e to the x. So our first factor is going to be the thing we started with, the e to the x log a. And then the second factor is the derivative of x log a, which is just log a, because that's a constant. So we get e to the log a times log a, and e to the x log a, rather, times log a. And e to the x log a, we saw was just another way to write a to the x. So we get a to the x log a. That's the derivative of a to the x. Kind of nice. And remember, this log a is just a constant. So what this is really saying is that every exponential function, I mean, e to the x is special. E to the x is equal to its own derivative. But other exponential functions are almost as nice as that. They're not equal to their own derivative, but they're proportional to their own derivative. The constant of proportionality is just the natural logarithm of the base. So that's another way you can say that. Anyway, it's a nice result. So anyway, that concludes my video on differentiating exponential functions. Thank you for watching. Long live math, and I'll see you guys next time. Bye.